All right, this is a video for Algebra 2 on rational functions, and we'll start with an introduction and then do a few solved examples. A rational function in general, the term for it has an origin from the word ratio, which refers to division, and we're really just thinking about dividing two polynomial functions. Okay, you are familiar with polynomial functions. Those are linear functions, quadratic functions, cubics, etc. Okay, and if we just divide those, we'll end up with a rational function. And I'm showing you some examples of rational functions here. X squared over x squared plus 1, the quotient of two quadratics. Here is a quadratic divided by a linear. And here is the quotient of two linears. Okay? One common theme throughout all of our work with rational functions is really being aware of when we're being asked to divide by 0. We're not allowed to divide by 0 in mathematics. It violates math law. And we're going to want to start thinking about what values of x might make these denominators 0, which would lead to points where our function might be undefined. So if a function does have a graph where there are maybe gaps or breaks in the graph, or locations on that graph where the y value is undefined, perhaps because you're trying to divide by 0, that would be a discontinuous graph, okay, a non-continuous graph. In contrast to a continuous graph. So a continuous graph has no value of x that makes the denominator 0. Okay, you can trace it with a pencil and never have to lift up your pencil to follow the entire curve. Whereas a discontinuous graph, there are breaks, maybe asymptotes or holes in the graph that would require you to lift up your pencil to continue tracing that graph. A point of discontinuity is simply any break in the curve, and again, that could be a asymptote, which we'll look at, which is also known as a non-removable discontinuity, and that could be a hole, which is known as a removable discontinuity. So let's look at a removable discontinuity first. I hope you can see that if x were to be 2, we would try to be dividing by 0. Okay? We're not allowed to divide by 0. But I hope you could also see that we could imagine canceling out those terms. We would be left with y is equal to x plus 4. Okay. If we simply graph the line y equals x plus 4, it would be a line with a slope of 1, intercept of 4. It would not be precisely the same as the original rational function we were being asked to graph. So when you are canceling out terms, when you are removing those discontinuities, you have to remember that x is still not allowed to be 2. So if we were to graph this line y equals x plus 4, we would want to add in a little hole at x is equal to 2. And I'll show an example of that in a second. A non-removable discontinuity is an asymptote, typically, and in this case, y equals x plus 4 over x minus 2. I hope you can, again, see x is not allowed to be 2 because we would be dividing by 0, but there is no cancellation that could happen above. Okay, so we would end up with an asymptote at this point at x equal to a vertical line that our curve would get closer and closer to but never intersect. Let's find some of those points of discontinuity, and often we're going to be doing that by factoring, okay, and seeing if we can cancel. So let's factor this one up top here, y equals x plus 3 over, that factors into, let's see, x minus 3 and x minus 1. So nothing cancels in this case. Okay, so there are no holes, no removable discontinuities, but we do have two asymptotes. And those asymptotes would occur at, are these lines. These are the equations of the asymptotes, x equals 3 and x equals 1. So to be clear, x equals 3 and x equals 1 are two vertical lines, okay, the asymptotes for this function. But if we were thinking about the domain of this rational function, we would want to say that x is not equal to 3 and x is not equal to 1. Okay? The asymptotes occur where x is not allowed to be for the original function. For this next one down here, y equals x minus 5 over x squared plus 1, we could think about what values of x would result in a 0 denominator. And trying to solve for x in this case, x squared equals -1. There are no solutions to that equation in the real number system. and there are in the complex number system, but that's out of our realm of interest at this point. So this is a continuous graph. There are no breaks in this graph. There are no locations where we would be dividing by 0. This next one, if we factor the numerator, I hope you can see that we have some cancellation that could happen, and then our function ends up looking like y equals x plus 1. Let's go ahead and graph y equals x plus 1. That's a slope of 1. There's a hidden 1 in front here, and then a y-intercept of 1 as well. So we can go ahead and graph that. But we need to remember that x is not allowed to be 4. X can't equal 4 in this function because, again, we'd be dividing by 0. So the way we show that is we graph a little hole at x equal to 4. Okay, so that would be a true correct graph of this rational function we're working with. It, for the most part, looks like the line y equals x plus 1, but there is a break in that line. There is a hole in that line because x is not allowed to be 4. The function is undefined when x is 4. Some rules for finding those vertical asymptotes, or maybe finding the breaks, the holes in the function. You can find those breaks by factoring and canceling if possible, but keep track of the original function. Once you cancel something out, it's not gone forever. You need to remember that you did that. Again, think about what values of x give a 0 denominator, and if they're not cancelable, you'll have a vertical asymptote at those x values. So for this particular example here, f of x is x minus 3 times x plus 2 all over the product of x plus 2 and x minus 4. So x minus 4 is not cancelable with anything up top, and so we have a vertical asymptote at x equals 4. Okay, so I can draw that in. We will have a vertical asymptote along that line, or that line is the vertical asymptote. So our function would approach that line, but never touch it. And we would have a hole at x is equal to negative 2. Okay, so somewhere on where x is negative 2, right here, somewhere on there we would have a hole. Wherever our curve would try to cross x equals negative 2, we would have a hole, but it would not be an asymptote. Finding vertical asymptotes, as an example here, I hope you can see that we have two vertical asymptotes. If x were to equal 2, we would have a 0 denominator, and if x were to equal 3, we would have a 0 denominator. So x equals 2 and x equals 3 are our two vertical asymptotes. Okay, and that's really just a matter of looking at these denominator terms, factor it if you need to, think about what cancel out with what can't cancel out from the top, and apply those values to your vertical asymptotes. Horizontal asymptotes, the rule is a little bit more complex, I think, but you might disagree here. But the rule is to imagine what would happen as x gets very, very large. As x becomes in the billions, trillions, mathematically we would say what happens as x approaches infinity. What's going to happen to y as x gets huge? And the way I like to imagine that here is, first off, looking at the x terms with the largest exponents, because that's what's really going to dominate. If we are squaring a billion versus cubing a billion, the cubing of a billion or a trillion or something larger will really dominate, and the squaring of that number won't really matter as x gets so large. So we can effectively ignore all the other pieces. So what I'm going to do for this first example is I am going to literally cross off and ignore the pieces of this function that don't have the highest exponent of 2 in this case. And so in this case, as x gets huge, y is going to get even larger. Okay, imagine 3 times a billion squared, 3 times a trillion squared. Y will just get larger and larger without bound, is what we say in mathematics. So in this case, there are no horizontal asymptotes. Simply because y just keeps getting larger and larger. There's no limit, there's no sort of cap on what y could be. But let's look at a contrast example down here, and let me actually undo that crossing out of those terms so we can keep track of that. But really what we did, we just looked at that term right there, that purple highlighted term. Okay, so for the second example, let's zero in on the term with the largest exponent. That's what's going to really matter as x gets huge. And I hope you can see as x gets large and large and larger, we're going to be dividing by a tremendously large number. And so when we divide by a tremendously large number, we approach 0. So in this case, we have a horizontal asymptote of y is equal to 0. What if we have this case where our two terms with the largest exponents sort of cancel out top and bottom? Okay, so again, to be clear, this 3x minus 1 and this minus 8, those don't really matter in the grand scheme of things as x gets large. But what if we have a term, an x squared term up top and a comparable x squared term down below? Here our horizontal asymptote is y equals 2/5. And I got the 2/5 by looking at the coefficients of those terms. And you can try this for yourself. Take this original function and plug in, evaluate this function for a tremendously large number, and you will see that y would get closer and closer to 2/5, but never actually hit 2/5 exactly. Okay, so these are all, or these last two that I just did here, those are horizontal lines. Okay, y equals 0 is a horizontal line. Y equals 2/5 is as well, and that would be those would be the equations of our asymptotes. So finding some horizontal asymptotes here, again, we are simply looking at the x terms with the largest exponents, and I'm going to highlight those here. Okay. So for the first one, we have two x terms with the largest exponent of 1, and the minus 3 won't matter in the grand scheme of things. We have 2x over x, and those x's cancel. We have a horizontal asymptote of y equals 2. In this second one, we have an x squared term down below, but no other squared terms anywhere. And so if we have a large number in the denominator, we have a horizontal asymptote of y equals 0. And in this last example, we have an x squared term up top, but relatively smaller terms down below. And so as x gets large, y will increase without bound. So no horizontal asymptotes. So let's apply this with one last example. This is a large video, and I appreciate your patience. We'll do just one example here. The key thing to keep in mind is I am not looking for exact precision for every point along these curves that we're trying to sketch. I'm looking for asymptotes, I'm looking for intercepts, and I'm looking for general shapes of the curves. So I think it's always beneficial to do any factoring you can first. So let's factor up top and down below as well. So up top, we have two binomials, x plus 4 and x minus 3. And down below, it's a difference of two squares, so x plus 2 and x minus 2. So right away, we can see that nothing will cancel, so there are no holes, no removable discontinuities here. But we do have two vertical asymptotes. The vertical asymptotes are x at x equal plus or minus 2. Okay? So I am going to graph those asymptotes first, and I will just go ahead and graph those in red here. X at plus or minus 2. So those are two locations where our curve will be broken. Let's then think about what a horizontal asymptote is, and I like to look at the original function to do that. And so the original function, we have a squared term up top and a squared term down below. So as x gets huge, the x minus 12 and the minus 4 become insignificant. We have a large number squared divided by itself, which is equal to 1. So we have a horizontal asymptote at x equal 1. So let's draw that in as well. So that's our horizontal, or excuse me, y is equal to 1. That's our horizontal asymptote right there. Okay, I like to think about a y-intercept next. So in other words, what is y going to be if x is 0? So let's plug in 0 for x, okay? And let me see how to do that over there. I'll do it over here. So y equals 0 squared plus 0 minus 12. And y equals 0 minus 0 squared minus 4. So I hope you can see our y-intercept becomes minus 12 over minus 4, which is 3. So we have a y-intercept of 3. Okay, let's find our x-intercepts now. So this was the y-intercept. We plugged in 0 for x. To find our x-intercepts, we're trying to find what are the values of x where y is 0. In other words, what we're trying to find is what are the values of x that give us a zero numerator. If the numerator was 0, that entire expression is 0, and y would be 0. So we're trying to find a 0 numerator. In other words, what we're trying to find is what values of x make that expression 0. Okay, so for our x-intercepts, it's analogous to solving a quadratic using factoring, and we will see that x is equal to -4 and x is equal to +3. Okay, those are terms that give us a 0 numerator, which would make y overall equal to 0. So x-intercepts, x is equal to -4 right here, and x is equal to +3 right here. So from this point, you're welcome to plug in actual further values of x and get more precise values of y, but I'm going to sketch in my curve because again, I am just looking for general shapes here, okay? So we need our curves to approach these asymptotes and never hit them, and they will look something like that. So there's a rough sketch of our function right there. So that one involved a lot, and we got through it though, so that's a good place to stop.